Hello, Physics 30s. We're going to go over this year-end practice test 2 here. All right, so let's try this out. So we got airbags. Why are they used? Well, obviously, they're used to increase time. How many times do I have to answer this question? But let's talk about why, all right? It's not the other two answers, right? Actually, just one second. I'm just going to say increase time. Number 3. The force is less and increased time, so it's got to be C. Sorry about that. All right, but the impulse is not going to be greater. Now, the reason for the impulse not being greater, it's a pretty simple little explanation, right? Because you have to think about what's happening. So remember what impulse is. Impulse is change in velocity, right? Or change, not change in velocity. It's actually, sorry, mass times change in velocity. Now, if I'm, heaven forbid, in an accident and I'm traveling 50 kilometers per hour in a car without an airbag or with an airbag, I'm going to come to a stop from 50 kilometers per hour to a stop. Oh, right? Oh, sorry. To a stop in both situations from 50 kilometers per hour. So my change of velocity is the same. My mass of the car is the same. So my impulse is going to be the same. This is going to be the same. This is going to be the same. I times them together, I'm going to get the same, right? This is going to be the same. Same squared, right? So it can't be my impulse being greater. But remember, this is also equal to force times time, right? So even though this ends up being the same on that side, if I increase the time, because that's what an airbag is doing, it's cushioning you, it's increasing the time. So time goes up, my force has to go down to keep it the same. So there we go. So it's got to be 1 and 3. Cool. Okay. A lot of information. Okay. I gotta, maybe I'm snappy, making this go a bit faster here. The magnitude of impulse experienced by this car. Oh, so this is a fun little question. I asked this question on some redo tests and stuff here. So I got this weird graph, this fun graph because it's below the x-axis. That's a negative direction, right? It's brought a car to a rest, so that's going to be important, right? So it comes to a rest. So I'm going to just look at this graph here. Got some nice little units here. This is kilonewtons. This is times 10 to the negative 1, right? So what I'm going to do is I'm going to snip this graph here. I'm going to analyze the graph. Essentially, we're going to find the area of this graph. This is a force times graph, force time graph. So once you have a force time graph, we know we're going to get the area of this graph. Just it's a given. So the magnitude of the impulse and the initial speed was. So the impulse is the area. So I'm going to go back here, and it comes down to a stop. Okay, that's important too. So my initial velocity is 0. So what I'm looking for here is I need this area, because the area is my impulse, right? And the area is going to be 1/2 base times height because it's a triangle. Now, it doesn't have to be a rectangular triangle, right? It doesn't have to be a right angle triangle. It just has to be a triangle where I have a height. So the height is going to be this perpendicular distance here. Let's go with this kind of greeny color here. So that's going to be my height. And then my base is going to be from here to here. So as long as they meet at 90 degrees, it doesn't matter if they meet at the end of the base or in the middle of the base somewhere. So the area is going to be pretty easy. So 1/2 base. So my base is going from 8, from 3 over to 8. So that's 5 times 10. So if I do the math here, 8 minus 3 times 10 to the negative 1. All right. And my height is going all the way up to 70, technically negative 70. All right. But 70 to 0. All right. So my height is going to be negative 70,000 newtons, right? You just put the 1,000 in there. Sorry, but my face is in the way here. Oh, come on. Oops. Okay, 70,000 newtons. Okay, so let's put that in there. So 1/2 times 0.5 times 70,000. So right now I could already cross off two answers. So it can't be, well, it can't be C and D. Right? So cross those ones off. It's got to be A or B. Now we've got to determine that initial velocity. So what we just found is my, let me just write this down, is my impulse, my change in momentum, this negative 17,500 Newton seconds. Now remember, that's going to be equal to final minus initial. So if I go P final minus P initial, my final is 0 because it comes to a rest, right? A rest. So my negative Pi, my initial momentum, is equal to negative 15 or 17,000, blah, blah, blah. I get rid of the negatives. So they turn to positive here. I'm just not going to bother writing them anymore. And here we go. Now, how do I solve for, because momentum is mass times velocity, I'm going to just divide over that mass. So my mass in the question is going to be, let me just see, got to go back here. Right there. 1,200 kilograms. So let's go back to my math here. So divide by 1,200 kilograms. And there we go. Divide by 1,200. And we get 14.58. Let me just write that down. I don't know why I do that, because I'm not going to say this anyway. It just kind of disappears into the void. But that would make this answer 15. So it's going to be A. Cool. A skateboarder whose mass is this is running at a speed of blah. They jump onto an initially stationary skateboard with a mass. What's the maximum velocity? So obviously the velocity is going to go down, right? It's not going to stay the same. So C and D are out of the question. You gain mass all of a sudden, because that's what's happening. You gain mass all of a sudden. Why would your velocity go up, right? Your momentum's got to stay. It's got to stay the same from initial to final. There's a few ways to do this question, but I always do this the before and after situation. So beforehand, okay. Oh, this is white. White on white doesn't really work too well. So beforehand, we have this guy who's running along. He's going to jump onto this initially stationary skateboard, which is 0. So the momentum of that is 0. So this guy who's running this direction, his mass is 50 kilograms. His velocity is 4.5 meters per second. So the momentum of that is 50 times 4.5, mass times velocity, is 200. Let me just write that down. 225 kilogram meters per second. So the sum of all the momentum on this side is 225 kilograms meters per second. But afterwards, they're going to be 1 now, right? They're going to be 1. Okay, so now they're together. So now the mass has increased. So now we're 54.2 kilograms. We don't know the velocity, but we do know that all the momentum on this side has to add up to 225 kilogram meters per, what am I doing here? Meter per second. Okay, so that's got to add up. So this has got to go here then, because this is the only object on this side. So this has to have all this momentum. Okay, so now we know how much momentum it has. I can take that, mass times velocity, find the velocity by taking this 225, divided by the new mass, 54.2. And we get 4.15. There we go. Not too bad. So let's go back to the questions. 4.15, that's A. Most of that could have just been done in your head, but whatever. What's the maximum spell of the green ball after the collision? Okay, so we got this horrific picture. I've done this one before. It's ugly, but that's okay. So we're going to do this again. Boom, boom, boom. Okay, so what's nice about this is that they've given us all these momentums and all these energies is ready. We're using from 4, 5, and 6. So we got a couple of questions with this. All right, so they come along, they hit each other, and then that white ball just kind of moves perfectly horizontal towards that rubber bumper over there. And the green ball goes down at this 75 degrees. Now, that 75 degrees might be there just to kind of throw you off because you don't know if that's right. Usually I just would cover that up and say, find that angle. Maybe we want to confirm if that angle actually is correct. And usually if the government gives it to you, then you can use it, probably. But in this case, I'm not going to use it because I have enough information not to use it. And then down the bottom here, it talks about immediately after the collision, the ball hits the rubber bumper. The white ball velocity after it hits it is 1.2 meters to the right. Sorry, before it hits it. So there's some time here. It's going to come along. It's going to hit that at 1.2. Immediately after, the velocity is 1 to the left. So it's going to probably talk about impulse there. Maybe talk about the force. But I don't know what that question is going to be yet. So how we're going to solve this first part, what's the maximum speed of this green ball, it's all about the x and y's. So I'm just going to try to get a nice spot here where I can snip this and start writing all the x and y stuff. Give myself some space here. Yeah, let's do that. Okay, so this white ball at the top here, what I'm going to have to do, because we're going to be adding vectors. So I want to know the momentum before, and then after. All right, you got to know these momentums before. I have to know that what do all the x and y's add up to. So I need to know what the sum of all the x's are and the y's for the momentum. What do they add up to? Right? Because all the x and the y's afterwards have to add up to those same numbers. So these are just going to be the same down here. But it's momentum. It's not velocity, but momentum. So we're going to deal with these momentum numbers here. So we got this 0.34 here. This ball is going down at an angle. So this guy has both x and y. What's nice about this ball here, 2 zeros, right? It's not moving. It's stationary. So that's good. So this top one here, I'm going to use a little bit of trig. So if I were to draw out the triangle here, that's my y, that's my x. So my x, I'm going to use cos. All right, so at this point, hopefully, I don't have to explain why, but that's sometimes the nature of this course. Sometimes you have to keep on explaining the same thing over and over again. All right, so we got this. Oh, so I probably need a sign convention. Let's say those two directions are positive, right? So 2, 6, 0, 4, 5, 5, 1, 1. I'm going to try to keep as many decimals as possible. I'm using a pretty junky calculator. Okay. So the y one, I'm going to do the same thing. I got my hypotenuse. I'm using that 0.34 times sine 40 degrees. And I get 0.218577787. Okay. So now, because the other one is actually adds up to 0 or a 0, so when I add them together, I get just these two numbers here. Remember, these are the momentums, kilogram meters per second here. So these are not the velocities. That would only work if the masses were all the same, because then they can divide the masses out of the equations, and then it wouldn't be necessary. But all the masses are slightly different. That's 0.17, that's 0.16. I can't do that. Okay, so then this momentum's got to be conserved, so this has got to be down here too. All right, so I'm just going to write this one down here. And this is what I would do, like if I were to do this on like a written response question or something. I would show as much work as possible. All right, you don't have to do that here because this is just a multiple choice question or so. So down over here, what I'm going to do is I'm going to quickly do my x and y's, but this one's just perfectly horizontal. So this is going straight across there. So the y is 0, right? And this is all, I'm looking at my momentum here. It's all that momentum is all x. Okay, so I'm going to use that information to find out what the x and y of this ball is down here. So that's what I want to find, question mark here, right? Because then I can put them back together and create my vector. And once I have my hypotenuse of that vector, I can change it back into a velocity. So I'm going to find the x and y down here. I know what they should add up to, right? So what I'm going to do, just on the side over here, I'm going to write out a couple of equations. So this is my x1. So I know that 0.24 plus whatever has to end up being 0.26045511. Then my y component is going to be kind of the same idea. 0 plus whatever, so I'm bored here, has to end up being 0.2185787 kilogram meters per second squared. Kilogram meters per second squared. I guess I don't need those units. So the y one's really easy. So since I know the y1, I'm just going to write this down on the bottom down here, because that's what I'm going to have to do. I'm going to do that over here. My x and y pieces. My y1 is just, I'm going to minus this over to the other side, and I get negative 0.2185787. And then my x, I'm going to do the kind of the same idea. I'm going to minus this piece over. So I'm just going to minus that over. Minus over 0 doesn't really do too much. But minus over the 0.24 number. So let's just do this again. My calculator goes, oops, sorry. Cos 40. Okay. Minus that number. So what I get here for my x, oh, sorry. Oh, this one, I'm not minusing over 0. This doesn't change the sign. Okay, that's still positive. And this one's still positive too. 0. Definitely, because it's going down. So everything's positive here. Because I said down was positive. Okay, so now we know our x and y's. I can put these back together to find the hypotenuse, because p squared is equal to x squared plus y squared. Just the Pythagorean theorem it up here. So I got this number squared plus this other number, which I'm just going to type in my calculator here. Take the square root of that answer, and we get an overall momentum to be 0.22575. 0.81. Okay, and then, because that's equal to mass times velocity, I'm going to divide over the mass. The mass of the green ball, you can't see it, but it is that one there, not the point, not the white ball. Okay. And now I can solve for that. So I'm going to just divide over that mass there. And I get 1.41 meters per second. Okay, so that's a lot of work there. Now, if I want to confirm the angle, I'm just going to do that quickly. Is it actually supposed to be 75 degrees? This has happened before where it's not. So if I were to try to figure out what that angle is, I'm going to use this kind of x and y. I'm going to use tan, my y value, over my x value here. I just want to double check. Should it have been 75 degrees? Okay. Could I have used that to solve this question? It's just going to take me a bit of time to type these numbers in my calculator. 75.5. Why do they do that all the time? It's not the, it'll be 75.6 or it'll be 76 or so. Oh. Don't trust those angles. All right. I want to just strangle some of these guys. Okay, never mind. Let's go back here. All right. I think if I use that number, if this wasn't a numeric response question, and it wasn't, then I would have still got the 1.41. But they asked me to find the angle. Anyway. The classic, is it classified as elastic or inelastic? I'm just going to say it's just inelastic. Is it isolated or non-isolated? Momentum is conserved in an isolated system, but is this collision? I would say this collision is definitely an inelastic collision. I don't know if I really like this question at all, because you're supposed to say momentum is always conserved in an isolated system. But I don't know. Just maybe because that angle is not actually the right angle. Let me just go back here. This is the maximum speed, right? Maybe because the angle is not actually 75.5, right? Then maybe the energy is not, maybe the system is not isolated because it's not 76 degrees like it's the maximum angle would be. Maybe some other thing has happened here. So it's definitely an inelastic collision. I know I didn't do the calculation here, but I can, right? So to find out if this collision is elastic or inelastic, I got to find this energy because they got all these energies here. So I got up here this energy of 0.34. All right, so I'm just going to go through here. So we got 0.34. We got this energy over here. Yeah, 0.34. Because those numbers just happen to be the same. We got this energy here of 0.12. Can I find the kinetic energy of my ball afterwards? And if my kinetic energies are conserved, it's elastic. 99% of the time, macroscopic things like this are not going to be that way. So, but let me just double check here. I already know the answer. I could just move on, but okay, so I got that. I'm going to take square my velocity. I'm going to times it by my mass. Divided by 2. So here, after I do my EK for the final ball here, the green ball, this is what I get. If I add that on to the 0.122, I get 0.28. So my EK total, this is after, my EK total is only 0.28126 joules, which is a considerably different number than what it was before. So, boop. This is definitely an inelastic reaction. Okay, so now this is why this information over here, where it immediately hits this ball, what's the impulse? Remember, impulse is change in momentum, right? So if I want to find the impulse down here, which is the white ball? Yeah, the white ball. So I need the mass of the white ball. The mass of the white ball is 0.17. Okay, so what I'm going to do is I'm going to snip this little part of the bottom here. Yeah, that's all I need here. Okay. Let's do a little bit of math on the bottom here. Now, what they're doing is they have this kind of going, it's going to the right and then it's going to the left. So we have to kind of watch out for a little sign convention here. So to find this impulse, we're going to have to go mass times change in velocity. My mass is 0.17 because this is the white ball. The white ball collides with the rubber bumper. And what's my change in velocity? So my sign convention, let's just say that to the right is positive, then anything to the left is negative. So this 1 point, remember this is going to be final, final minus initial. So my final, maybe I should do final first if I'm going to do final initial. Okay, so my final is going to be negative 1.00 meters per second minus 1.2 meters per second. That's minus a positive number, right? So times delete 2.2, negative 2.2, and I get a kind of a negative. So the reason it ends up being negative because it's going the other direction. So if this is to the right, then because I got a negative, that means this is going left. I don't know if that's going to be important here, but this means left. Maybe that's part of this thing. Let's see. We're looking for magnitude or not? Oh, it is definitely. So it's definitely going left here. 0.37. Yep. So it'll be C. Okay. A negative electrorod is held near but not touching a neutral electroscope. Then it is grounded, and next the connection between the electroscope is broken and the rod is removed. Which will find best to the final state? Well, it's not going to be B, all right? because that would mean that the charges haven't redistributed, right? This would be like when it's close to it. Right? A looks like it's neutral. And the whole point of this is to charge it. And because what's happening here, we held a negatively charged rod. So a negatively charged rod comes near this thing, right? What that's going to do, it's going to push all of the negative particles that are inside the electroscope down and into the ground, so off this thing. So it's going to end up being positive overall. All right. Remember, in induction, this is charging by induction. It changes, right? It changes its charge. It's the opposite charge. So, D. Which of the following is not considered an observation electrostatics? A torsion balance can be used to measure electric forces. Not consistent with observations. I guess it could be, yeah. Right? Can we measure electric forces? Yeah. Electric forces are generally greater than gravitational forces. That's true. Yeah, you can overcome gravitational forces pretty easily with electric forces. Charged. Actually, no, just a second. It really depends. I don't know what B. I'm going to go back to that one. Charged objects can exert force of attraction and repulsion on a neutral object. Just attraction, actually, which I find is not consistent. So this repulsion one really kind of throwing me off. So this, I don't like this idea, this repulsion. Okay? So I'm going to cross that one off. As one charged object approaches the second charged object, the force exerts increases. So that's true. That first one's true. Electrostatic forces are generally greater than gravitational forces. Depends on what you're talking about, but I think it's this one here. Charged objects give a force of attraction and repulsion. Is that like an overall? Because it is attracting the positives and repelling the negatives at the same time, but overall, it's going to be an attraction because of that charge distribution. I don't know about that one. That's a weird one. That's question 8, right? I'm going to pick C. I'm just going to finish this test off here. Let's say this. What do they say C is? Oh, that's what they say it is. So, okay, I'll go with that. I'll kind of go back to this and return to the test. Okay, so, yeah, it really depends. This is generally greater than a gravitational force. So you talk about like the microscopic world, then yes. Yeah, it's way stronger, right? But maybe these larger objects, gravity's going to overtake. It's a poorly, I don't like that question. I'm just going to skip it. Sometimes you get those questions. Sometimes it's just a weird question. All right. 3 charged objects here. Based on the information given, what are the direction of the net electrostatic force? We're going to call that E. And the first one is what is the electrostatic force? No, it's a lot of work, but what's really nice about this picture is that all the charges are the same and all the distances are the same. Makes the math easy. Okay, and you'll see why in a second here when I snip that up. I'm going to get the directions in there too. Okay, so what's really nice about this is that, like I said, those charges are the same. So if I go with this red one here, positive and negative, they're going to attract each other. So there's going to be an overall force this direction, which I can find pretty fast. Fe is equal to KQQ over R squared, right? Everything's in, oh, no, not everything's in the right units here. K, I don't care. I'm not going to write that out, but that's 8.99. This charge, I'm not going to write any of the negatives in here because I know which direction it's going. I drew it. I don't have to put the negatives in here to show them, oh, it's a traction force. You don't have to do that. But this times 10 to the negative 6 I had to do. Right? And there's 2 of them. I guess I could have squared this number, but I'm just going to write it out twice. And divided by 2 meters squared. Make sure you square that number. And I'm going to get this force. So it's going to be a 45-degree angle, and you're going to see in a second why that is. Okay. So we get this force, 0.03596 newtons. And if I did this all over again, say with this force, which is going to be a positive, negative, I would get the exact same thing, 0.03596, because the math would be exactly the same. I don't see why the numbers would end up being any different. Okay, so now we know those, and this one's all y, this one's all x. I can just go down here and put them all back together. So x squared plus y squared is equal to this overall net energy, net force, sorry, squared. So my F net is going to be this number squared plus this number squared. Take the square root. So I get, not squared, sorry, 0.050855 newtons. And because one's going down and one's going left, my overall net is going to be off in that kind of direction there. Okay, so that's 7. Okay, so let's quit out of this. So what do they want here? A, B, C. Okay, so they want this to be 5.1 times 10 to the negative 2 newtons. So 5127. 5127. 5127. Perfect. Next one. Let's see what we have here. In field theory, electric fields are defined, or sorry, defines electric fields as force on a charge. That's, no, that's not a force. It's not a force. Energy, attraction, repulsion. No, it's not energy. A region in which a force could be experienced by a charged object. That is true. That's what it means. It's like I put this calculator in this region right here. And the reason it has a force on it, even though it's not accelerated, is because it's in a field. That field is still there, even though the calculator is not there, right? Now there's a force there because there's another mass there to experience it. But the force, the field is still there. There's no force, but there's a field there. But it could experience that. So I'm going to call that C. Electric field at this location from a positive charge. Is there a formula for that? Oh, look at that. Force divided by Q. No. Oh. It's right there. KQ over R squared, guys. So I don't really want to type in my calculator. This question is just too easy. KQ over R squared. Okay, so I know it has to be C or D. But because it is a positive charge, remember the definition of positive? It's out from the positive, right? Out of the positive, because that's the direction a positive charge would go. So away from the point charge. Cool. 3 identical spheres. They are sitting around here. They get touched a bunch of times. So these kind of questions here, what I like to do is draw out a little grid. So that's what I'm going to do. Okay, so we have covered the answers for now. So we have 3 charges here. So we have charge 1, which is 4, positive 4. Charge 2, which is negative 2. I'm not worried about the micro part of this. And charge 3 is negative 4. Okay, so if they're identical and they touch them and separate them, what they do is they just redistribute the charge between them. All right. So when I touch 1 and 2 together, my overall charge is 2, and then I separate them, and now they each have positive 1, negative 4. Then I'm going to take 2 and 3, touch them, and then separate them. So 2 and 3, I would have a negative 3 charge, so negative 3 divided by 2 is negative 1.5, negative 1.5, and this one didn't change. And then I take 1 and 3 and touch them. So that's a half each, right? Negative half. Negative half overall, and then I'm going to separate them, and that's a quarter. So a negative quarter of a charge. This middle one I didn't change. Negative a quarter. All right, so that's C. Is that an answer? Hey, negative a quarter, C. Boop. All right. Which of the following best describes the electrostatic force on an electron as a function of its distance from a negatively charged plate? So they're talking about plates, right? So this is not that formula there, KQQ over R squared. That would be just from a negatively charged particle, just another particle, right? As you get further and further away, that force is going to decrease, not increase. None of these describe that situation. Why would it, as you get farther away from it, would the force increase anyway, right? But because we're in a charged plate, that field is constant through a lot of complex, like calculus and lots of charges and stuff. But that field is constant. No matter where you are inside that field, the field is the same, or between the plates, the field is the same. And because of this other formula, right, I can't move my head in the right direction, right there, the force is the same. If my field's the same, my force is the same, so this has to be D. Oh, this Google file. I'm just going to close this down. Why is that there? Okay. Millikan here. Millikan type apparatus. We got a oil droplet. Is it suspended? Oh, it's moving at a constant speed. Now, if it's moving at a constant speed, that just means my F net's 0. So it's got to be A. Nice constant speed. Okay? Not accelerating. Remember, F net's equal to M times A. If the A is 0, then net. Okay, that's it. And then what's the charge? Okay, so to figure out the charge, what we're going to have to do is use that information that this is moving at constant speed. So my F net is equal to 0 because M times A is equal to 0. Okay. Because of that, the forces that are acting on this, which is gravity, and the electric force have to balance each other out. Because Fe plus Fg, which is F net, remember the sum of the forces is equal to 0. That means Fe is equal to negative Fg, right? I'm really just worried about the magnitude of these. So this is going to be mass times gravity. This is going to be, I can move my head sideways, E times Q, right? And I'm just looking for Q, right? I'm just worried about the magnitude. The magnitudes are the same. I can just put it here if I want. So magnitudes, okay. So mg divided by E. I think they gave me everything else. What is E? The horizontal plates are this far apart. We have a voltage. So we got to determine what E is first, right? So maybe I'll go over to this other side over here and determine what E is. The electric field is going to be my voltage divided by my distance. So remember, for this formula to work nicely, the voltage and the distance have to correspond to each other. So they have to be, if the voltage is the full distance, then the distance has to be the full distance. So this is going to be the 1,000 volts divided by 0.2 meters, right? Because that's the distance between the plates. So 5,000 volts, or 5,000 volts per meter. Okay, so now we know that. I could take that over to this other side over here with my mass. .81 divided by this electrical field. I get 8.04. What is that answer? Is that on here? So it's got to be A. Yeah, it's got to be A. Weird. Okay. Oh, I like this one. Okay. Two wires are near each other. Which one is the correct one based on the current flowing in the same direction? So the first part is just your hand rule. These electron flows, so use your hand rule, put your thumb in the correct direction, and then wrap your hand around. So I can see that C and D are wrong, right? So C and D are wrong, right? Based on my little hand rule here, we're just going to wrap around. You can see how my hands are wrapping around here, using my left hand. So it's got to go in that clockwise direction. Now, remember, then when the two things, what's happening here is that these fields produce these kind of weird little mini magnets that you can't, these invisible magnets that you can't see. So if I were to zoom in to this section right here, and I were to draw in what we call these little mini magnets, all right, so right here, draw a little magnet right here, and draw a little magnet here. This line is coming out the top, so that's going to be a north, and this line is coming out the bottom. That's the north. There's my south. There's my south. So a north and a south, what are they going to do? Because the north and the south are on the top and the north south on the bottom, they're both going to attract each other and they're going to move in towards each other. So this is going to cause an attraction. So it's got to be B. Okay, based on my hand rule and knowing that they're going to attract. All right, which of the following best describes what's happening here? So remember, electrons come out the negative end. So I'm just going to, oh, you can see that they flip. Well, that's kind of mean of them. Okay, so I'm just going to snip this out. And we're going to draw in a couple of these and see which one makes the best sense here. All right, so if the electrons come out the negative end, so these are the electron flows here, and this one here, my electron flow is going the other direction, right? Then watch very carefully about the curl of this wire. So let's start with the first one. Let's see if that's right. I think I just saw the answer, but whatever. Okay, so you can see here, this is curling around the bottom. So my hand has got to go up and around the bottom, and my fingers curl around in this direction. That's the way my fingers are going. They're going across the top, over the front, and then down. And when I do that, I get my north on this side because that's the direction my thumb is, and then the fields here are going the wrong direction. Okay, so this one down here is kind of the same idea. I get the north on this side because my electrons are going here and they're going over the top, just like the last one. So it mimics that one up there and they're going the wrong way. So can't be those two. I can't remember which of those are. A and C. It's probably going to be this one over here because that's what I saw. My hand's going to go over the right side here. It's going over the top. So my electrons are going over the top like this, around the back, and then down. So this is going to be a north here, and this looks good. I'm happy. This one here, you can see is going the other way, and this would be the north here, but then these things are pointed the wrong way. Okay, so it's got to be that one over there. So let's go there. What's that? Is that B? I can't see. Yeah, it's B. Cool. Okay, so we had to use this for questions 2 and 16. Numeric response to question 2 and question 16. Okay, the radius of the circle path is what? Okay, let's just do that. And 16, I believe, is like which direction is it going? So radius, circular path, Tesla's, direction, it's an alpha particle. Okay, so we got lots of good information here. Let me just snip the piece that I want. Right there. Okay, so because it's going to travel in a circle, what I can say is that my FC is equal to FM. We got M is equal to AC. That's what just Fnet is. FC is just an Fnet. FM is QVB. We just have to find the right formula. We have speed here. So for A, I'm going to use the V squared over R formula for AC, not the other one because I don't have the period. And we're just going to solve for V here. So cross up one of those V's, like divide both sides by V. Well, not solving for V. What am I solving for? R, the radius, because I already have V. So I got times the R up to that side and divide the Q and the B down. Okay, so alpha particle, charge in an alpha particle. So we got all this information on our formula sheet. It just kind of sits there on the top of that formula sheet there. Alpha particle is 2 e's. So just remember that this is 2 times, so this is that 3.6 times 10 to the negative 19 coulombs. We got 0.1 Teslas, that's a reasonable number. We got this nice velocity. All right, and we got the mass of an alpha particle. Make sure it's in kilograms. Negative 27 kilograms. Okay, So put them all together. 6.65 times 10 to the negative 27 times 2e5 divided by, I'm going to put this in brackets here. Make sure when you're dividing by two numbers, you divide by two numbers. Don't make a mistake of dividing by one number and then times by the next by accident. So I get an answer of 0.0415625 meters. I believe it's in meters. I think I got all these units right. Yeah, nothing weird. Okay, so let's go back here. So what do they want? Oh, they want it in scientific notation. 4.1, going to round that up. 6 times 10 to the negative 2 meters. So 4162. 4162. Perfect. 4162. Awesome. Now, yeah, so this is the direction one. This is, I remember this one. So this is an alpha particle. All right, we've been using the left hand quite a bit often because that's all about electrons, but alpha particles are positive charges. So what I'm going to have to do is orient my hand. Remember, this is your hand. I'm going to use my right hand. Okay, I'm going to put my fingers in the direction of the magnetic field, which is into the page. So it's kind of into the page. I put my, can't really do this. I kind of bend this way. I can see my palm is kind of facing upwards already. So I put my thumb in the direction the particle is moving, and my palm, or if you do it this way, these fingers represent the force. So it's going to like being pushed off in that direction. So if I orient my hand in the right way, I can see it's going to be pushed off towards number 2. So that's going to be the direction of the force, towards number 2. And then the circle, like this is kind of weird. I could just automatically cross off half these answers. And then if it's forced off in that direction, that's where the center of motion is going to be. So it's got to be at 2. It's going to be forced towards 2. That's the direction of the force. That's where the center is. Yeah, it's kind of a weird question. Oh, this is a fun question too. Okay. Now, they like to do these kind of questions, right? You kind of think about a lab that we might have done in lab, or maybe not, right? We try to do them all, right? But sometimes they just make a new lab. That's okay. Does the length of the wire affect the magnetic field? So, okay, we have over here. What's my research question? So we can pick a bunch of these. A lot of them are going to be right answers. So we can pick one or more. Doesn't really matter. There's lots of different answers you can have here. So we choose one of these. And then which one would I manipulate? What's going to respond? And what must I control? And they've got some variables down here. Okay. So say I chose research question 1. Let's just do that. Like, just pick a research question and see if it works, right? Maybe one of these doesn't actually work. Maybe something we can't change here, right? Does the length of the wire in the magnetic field affect the force? Okay, so they're saying that does the length, if I change the length, what happens to the force? So they're saying literally in that sentence, what if I manipulate the wire, what happens to the force? So 7 and 6. And then what do I want to keep the same? Either 8 or 9, right? Maybe I'll keep 8 the same. I don't want to see if I change that by accident. Or the current in the wire, keep that the same. Just make more loops or something. So that could be an answer. It could be 9 on the end, right? But I could have picked any of these other ones too. Maybe any of the other ones. Like, does the magnitude of the current affect the force? So if I want to do that one, I can go back here and change it. So I can go back here and go blah, blah, blah. And do, let's see. So does the current, so 9, does it change the force? 6. Sorry. So I picked 2, right? And then 9 and 6. 9 and 6. And maybe keep the strength of that the same, or the length of the wire the same. Does the strength of the C-shaped magnet affect the force? It's just all the same. Pick one of them. And then make sure you kind of just line up the manipulated variable, which is what you change, or it responds, and then what's left over is just what's left over. And those is just, you have an option of 2 of them. Now, the one we can't do is 5, I think, the orientation of the wire, because they don't give me the option of one of the variables of changing the wire, right? So I probably couldn't pick 5, but I could probably pick 4 or 3 or any of these other ones. I'm just going to pick this one. I'm going to go next one. Okay. Which best illustrates good result and main effort described? Okay, so what do they want here? This is a weird question. Not weird. So electron is traveling. Oh, I don't want to hit that button by accident. Okay. Okay, an electron is traveling to the right. It enters in the region. Oppositely charged parallel plates. We've got a positive on the bottom, so that means it's going to be attracted towards the top, right? Opposites of charge, or opposite charges attract, or likes of repel, so it's going to be repelled from the bottom. So this is going to go fly upwards. That's projectile motion, parabolic, right? Parabolic motion there. So this, another electron travels between two bar magnets and experiences the force initially in the same direction. And they say initially, because when you enter a magnetic field, it produces circular motion because the force always changes direction. And this one produces parabolic, the first one. So they want to know which one of these produces the initial force upwards. Right? Because this is going up. Because a positive and negative attract. So which of these over here produce an upwards force? Okay, so we've got to put our hand rule here. Got left hand, north to south. Okay, so it can't be C. It can't be D because they're going the wrong way, right? Into the page, out of the page. So that's not going to work. So it's got to be A or C. You got to look very carefully at those N's and S's. You know, those are really hard to read sometimes. But those are kind of trying to do a three-dimensional picture where they kind of out of the page and then this. So if I were to kind of orient my hand in a way, then I could see that in B, the force is down, right? Because it's going from north to south. My thumb is in a direction, and my palm is downwards. So if I want an upwards motion, it's got to be A. Okay, in a Michelson type experiment, 12-sided rotating mirror, 10 kilometers apart from each other. What's the lowest frequency that goes? So remember, this is one of those formulas which are not on your formula sheet because it's just too specific, even though all these other formulas are pretty specific too. But remember, this formula is that 2DNF formula. The reason we use 2 is because it's got to go there and back. So the speed of light is equal to 2DNF, right? 2 times the distance, got to go there and back. N is the number of mirrors. The frequency is what we're looking for here. So frequency. Now, there's other ways to get this formula, but it's just one of those ones you just remember because they always ask this one, right? So 2D over N. And they don't tell you what the speed of light is in the question. Just assume it to be 3 times 10 to the 8. What's on the formula sheet? All right, so make sure when you divide it by all these numbers, you actually divide by these numbers, and that 10 kilometers is actually 10,000 meters, and you times it by 2, so it's 20,000 meters. And you got 12 mirrors. So I get 1,250, or 1.25 times 10 to the 3. So 1253 hertz. Okay, 1253. 1253. 1253. Okay, there we go. A vacuum in a particle, or in a vacuum, a particle has a mass of this and a charge of that. Accelerates from rest through a potential difference of this. What is the final velocity? Okay, so the key here is from rest, all right? So if it's from rest, I'm gonna get a part of my neck on this picture here. I don't think it's just a particle. What's the final speed? Oh, it has a charge. Okay, a particle with a charge. Okay. So we're going to use that change in velocity formula. That's out of view on my picture here, but it's going to be delta V is equal to delta E times Q. Now remember that delta E is either kinetic or potential, right? Because if one goes up, the other goes down. So it's just the change in the energy because of conservation of energy, the work energy theorem. It doesn't matter which one we're talking about. So when I find this change of energy, I can just say this is the kinetic energy, and then I go final minus initial. And because it starts from rest through this electrical potential, my initial is 0 because it starts at rest. So when I do this calculation, I'm really just getting the final kinetic energy. So I got the voltage, 1 million volts, that's a lot, times its charge. All right. You get this nice number, 2. So I get 2 joules of energy. All right. And remember, this is kinetic energy, so I can go 1/2 mv squared, rearrange it, so I could times it by 2, divided by my mass. So it's times that number by 2, divided by my mass. Nope. And take the square root. So I get 1,000. Well, that's a really nice number. So what does that end up being? 1003. 1003. All right. So again, another one of these cool little experiments here. So this is like a little machine that measures the index of refraction of material by using the critical angle. Right? So we got a prism, which has a known value. We got this light traveling through. So we got the index, the incident angle. And we're trying to find what the critical angle is. And this machine just kind of tells us that at this angle, it produces this index of refraction here. So this is the gemstone index of refraction here. Oh, can't write it, but it's I'm going to read into this here. I got wavelengths here. I might want some of that information there, so I'm just going to do that. I don't think I need anything else on this picture. All right. So let me just grab this information right here. Not drawn to scale, which makes sense. Okay. So how does this work? So over here, I just want to measure what this index of refraction is. So this is going to be 1, 2, 3, 4, 5. 1, 2, 1.525, right? Because 1.5 and this is 1, 2, 3, 4, 5. So this is 1.51, 1.52, 1.53. It's halfway between them. So this is my index of refraction. So I got index of refraction 1.6. I got this index of refraction 1.252. They're looking for what the critical angle is. So remember to find the critical angle, you make theta, the second theta, the refracted angle, 90 degrees. All right. So we just put that into our formula here. We got N2 over N1 over sine 1 over sine 2. All right. So remember those guys flip. So if I say that, let's say 2, this is when up here is 2, and this guy down here is 1. It's hard to do that because it's white. Down here is 1. All right. Then I got 1.525 over 1.6. I'm looking for this angle, call that the critical angle, and I'm going to make this angle 90 degrees. Now, if I do this wrong, you just can't do the math, and you just flip the numbers over. But sine 90 is 1, but really just rearrange it. Find cross multiply, divide, whatever you want to do, and make sure you take that sine inverse. All right. So you go sine inverse of the 1.525 over 1.6. Like I said, if they're upside down, it'll just give you a math error. Just flip the numbers over. So here I got 72.4 degrees or so. What do they want here? Critical angle, 3 digits. So, okay. So I get 72.4, right? Cool. Instead of yellow, blue light is used. The critical angle would be what? Okay, so remember, blue light is going to refract more because it's shorter wavelengths, which means It's going to have a higher index of refraction. Yeah, because it's going to slow down more. Is that right? Just a second. Oh. I don't know what's going to happen here. Relative to the blue light, what's happening? Oh, when the blue light is used, the critical angle would be blah. The relative wavelength of blue light is that. It's kind of weird because it's going into two different materials. It's not air versus something else. It's going to go slower. I don't know if I like this question because they're not giving us like what's the index of refraction for, what's the index of refraction for the blue light, right? For this prism, they give us the index of refraction there. That's most likely for the yellow light because the index of refraction changes. And how does it change based on the material? I don't know if that information is given to us here. I don't know what they would have asked on this question. I know the wavelength of blue light is shorter, so it's got to be B or D. This is a weird question. Okay. Instead, blue light is used. Blue light used, critical angle. What? Yeah, but it wouldn't give us the same number. The wavelength has changed. Oh, maybe I could do it some other way then. No, this wouldn't work either. Because as it goes in, the wavelength's going to change as well. So I don't know what the wavelengths are. I can compare the wavelengths, but I can't compare angles. Or can I? Okay, so I don't know what they're trying to do in this question. This is not a really fair question because I think what they want us to do is say that, oh, this index of refraction is 1.6, no matter what type of light it is. If that's the case, then when it goes in the other material, it's going to have a higher index of refraction because it's going to slow down more. It's going to bend more. So its index of refraction is going to be higher, like 1. Oh, it's going to be higher or lower? Because it's going to slow down. It's going to be shorter wavelengths will bend more. So they slow down more. And to slow down, you need a higher index of refraction. So if I have a higher index of refraction, and I do the math, so let's imagine it goes a little bit higher, like 1.55. So if I do the sine inverse of 1.55 over 1.6, I get 75. So it's actually larger. Oh, it's going to speed up. I'm really pissed off at this question. Because this question just doesn't work based on the information that we know. Because they're not giving us enough information. They're not telling us what the index of refraction for blue light is. They're telling us what yellow light is. I'm assuming this is designed for yellow light. So that's going to change because every material has different index of refraction for different colors, right? Blue light will be going slower in both of these materials, so that both the index of refractions will change. So how are we supposed to know what those new numbers would be? It's just because they give you some numbers, maybe you can use those to help you compare them. Maybe you could think of it as a way of saying, like, because it's blue light, it's going to have a bigger difference between the two because it bends more. So its index of refractions must have a bigger difference as well. So if you just pick two things that have a larger difference in them, like 1.6 versus, and the other one would be like or that one would be 1.7 now because it's blue light, and I go 1.55 or something for the other one, and then take the sine inverse, I could see that being smaller, maybe 60 some degrees. Yeah, so I think it's going to be smaller and shorter. I'm just going to go with that, smaller and shorter. Okay. Historically, light used in refractometers produced by burning sodium because it produces a yellow flame. Here it comes. What is this energy level at the top here? So I know it's going to be negative, right? So negative. Put a little negative there. The reason I know it's negative because they're using negative energy levels over here. And it's going to be a lower number because it's going closer and closer to 0. This is going to be its higher. But it'll work out if you do the math of this one. Like if you do like the final minus initial stuff. All right? You'll figure out exactly what it is. So there's going to be a change in energy here. And the change of energy as it drops down, that's going to be a minus there. All right, so let me just get a color here that would work nicely for this one. Face is in the way again. Okay, so as it drops down, the energy is going to change, and it's going to change in a negative way. So this is going to release a photon of hc over lambda. I'm going to put this in electron volt version. So 4.14 e to the negative 15 times 5 divided by its wavelength. 489 e to the negative 9. Okay, so I get a change of 2.10865 electron volts. Now, that's the electron that's being pushed out. This change is a negative change. So this change here is a little star, negative 2.10865 electron volts or so. So using that negative change, negative 2, because remember change is final minus initial. Yeah, there's a bunch of decimals there. 8658 blah, blah, blah. Electron volts. And then this is going to be final. My final is negative 1.54 electron volts. We're trying to find final minus initial. All right, it's final minus the initial. All right, I'm going to rearrange this to get my other number. Yeah. So I'm going to add over this number. So I'm going to add that over. Plus 1 point. I get a positive number, but remember this is going to be 3.0313 electron volts is equal to negative EI. So EI is negative 3.03. Okay, let's go back to your questions here. Oh, what do I want? Oh, I don't want the decimal. Okay. That's weird. Oh, no. What did I just do? There you go. They don't want to put the decimal in there. Okay. Image formed by an object placed in front of a convex mirror. Focal length of that. What are its... They use an upright and inverted now. They used to use erect and inverted. They're no fun anymore. Okay, so we just want to figure out, using a convex mirror, what that focal length means, right? So if the focal length is 10, because it's convex, it's negative 10 centimeters, all right? So that's why it's negative, it's convex, all right? An object is always positive, so 12 centimeters. We just leave it in centimeters here. We just want to find what DI is, and then find out what M is to figure out its types, its characteristics. All right, so we got this formula here. All right, I can put in some numbers here. 1 over negative 10 is equal to 1 over 12 plus 1 over DI. So we're going to get a negative number here for sure, right? Convex always produces a virtual image anyway, so I could have crossed off the reals. But I'm gonna do the math anyway. 1 over 12. What was that, my wife? Oh, she loves me. Okay. So I'm going to get di. I'm not going to go through all the steps here, but remember to do that 1 over stuff to get this. I get a di to be negative 5.4545 or so. Just keeps on repeating. Centimeters. Okay. Then what I'm going to do, because the negative right now tells me it's virtual, right? This tells me it's virtual. Right. Then I'm going to get my m, negative di over do. 2 negatives make this a positive, so this tells me that this is upright. So they're changing the wording. I have to go back and double check they changed the wording on them. Okay. So upright, erect, same thing. I think you can figure that one out. And then I'm going to have this divided by its do. Do is 12, right? So divided by 12 here. And I get a fraction, technically, of 5 over 11. That's less than 1. So all of this tells me it is diminished, or now it's small and large. What is they? Just changing words on me. But this is definitely smaller or diminished. All right, I have to go back and double check to see if they actually change those words on me. Okay, but everything makes sense. So it's virtual. Can I cross some of the stuff off here? Boom, boom, boom. It is upright, and it is definitely smaller. There you go. But I could have done that question without any math if I remember that that was always the case. It's always going to be virtual, upright, and smaller. Those are like security mirrors. We've seen those before. So I could have done that without any math. What was that? Virtual, upright, smaller. Done. A laser pointer. Where am I on this test so far? 20. Oh, we've got quite a bit of questions left here. A laser pointer emits red light and has a wavelength of 6.5 times 10 to the negative 7. A different one emits a green light, shorter wavelength, makes sense. Instant on a diffraction grating, the interference pattern produces this. The angle for the red light is that. What is it for the second order for the red light is that. And what's for the first order for the green light? So what they have in common is the diffraction grating. So we got to figure out what is the D of the diffraction grating, because then I can use that on the second part. So let's go back to my snipper here. Okay, so we're going to use some information here to find out. So we're going to use, first of all, we're going to use for the red, right? So for the red light, they give us an angle. So I'm going to use lambda is equal to d sine theta over n. So they give us n here to be 2. We got theta to be that. We're looking, and we have the red wavelength up here, right? That's red. So I'm going to solve for d. So I'm going to go n lambda over sine theta. Make sure your calculator's in the right mode. This is easy peasy. So I'm going to use the 2 because they talk about the second order maximum. I'm going to use the 6.5 times 10 to the negative 7, and then we're going to divide it by sine the 13.3. Done. So I get a d value of 5.65095 times 10 to the negative 6. So in the same apparatus, I'm not going to change it. I'm going to use that same d value, and I'm going to find, what am I finding? Angle. So I'm going to take this formula again, I'm going to rearrange it for sine theta, n lambda divided by d. And then I got to take the sine inverse of that, right? N lambda divided by d. And that's good. So this is going to be a first order. So this n here is equal to 1. I got a lambda up there, 4.8. So, because I don't have to do too much with the 1 times 4.8, negative 7, divided by this d that we just found, and I'm just going to take the sine inverse of this angle. So I get 4.87 degrees. I wonder if I could have done that without any math. No, they're all, I couldn't do this. It would, obviously it wouldn't be 13, right? But all these other angles are a little bit smaller, so I couldn't really do any extra math there, but it's 4.8, so it's going to be D. Boom. Okay. Some phenomena is demonstrated by EMR, diffraction, interference, Compton scattering, photoelectric effect. Which of the following describes particle model? Well, that's Compton photo effect, obviously. 3 and 4. It's got to be the last one. That's it. It's done. 3 and 4. Those are the particle model ones, right? That's Einstein's idea that the packets of energy 1 to 1, and then Compton is like they have momentum and they scatter off. And then these other two are just Maxwell's predictions of wave models, diffraction, interference. That's BD. Yeah, okay. Which of the following types of EMR is the greatest energy? X-ray. Yeah, X-ray. Shortest wavelength of all these. No, they don't seem to be in order, but yeah, X-ray. Okay. Remember, if gamma ray was on there, then that would be the next one, but it's not. Okay. Light incident on a right angle prism here is shown. What's the angle of refraction shown above? The index of refraction. I'm assuming this is it's in air. That's good. Okay, so this is a question we can do mathematically. It's not like the other one that was like almost literal BS. Okay, so to figure out the index of refraction, if we know this is air out here, we just set up the Snell's law. Remember to do that. We're going to go N. Let's just call, we're trying to find N2 here. This is 2. So we have air, and 1 being air, so that's just 1.00. We have the angle 1, so remember that's going to be up here on the top, and then we have this second angle down here. Yeah. So cross multiply, divide. Sine 30 divided by sine 17.8. I get 1.64. What's that? Oh, that's B. There we go, 1.64. Easy peasy. In a classroom investigation, they observed that ultraviolet source on this incident polished metal, the leaves collapse. Of a charged electroscope collapse. They were charged originally, and then they collapse. Probably charged negatively. Based on the observation for the phenomenon that is this, would be the photoelectric effect. So the radiation hits that and ejects out the electrons. The electrons that were on the metal would come and take over that spot, and they would collapse. And if this is going long enough, they would come back out because eventually it'd become positively charged. And up they go. That's not too bad. That's an easy one. What's the maximum speed of the photoelectrons emitted in this experiment? Oh, we got some stuff over here I didn't see. Is that on the previous one too? Nope, just on this one. Okay. So we want the maximum speed. Okay, so remember this is going to be using the formula that we don't have, right? Let me just write it out for you. We gotta use it for the next 2 questions. Okay, so the photon energy has got to go somewhere, right? So this is my photon energy. It goes into the material. Yep, and remember that's got to be absorbed. 1 photon goes in and gets 1 electron, and it's used to dig itself out with the W, and then what's left over goes into EK. And if I can find the EK, that's equal to 1/2 mv squared, and v is equal to the square root of 2 EK divided by m. And these are electrons. Photoelectric effect. It's all about electrons. They didn't even mention this, or maybe they mentioned it in the question. All right. So they give us the work function. That's awesome. They give us the wavelength, so we can find the energy of this photon. And then I can use that to find that EK. So I don't want to use too many of these things. So the first step here, I'm just going to use the H. That's the 4.14, the electron volt version of this number. And its wavelength. Okay, so I get an energy here, 3.15 electron volts, 2.5 electron volts, and then I get my EK. So I get my EK minus this over, minus 2.5 here. I get an EK of 0.605 electron volts. I'm going to quickly change that to joules now. So I'm going to use my electron volt number and change this to a number of joules. Because remember, in the EK formula, I can only use joules. So this is going to be 9.68 times 10 to the negative 20 joules. And then I can use that in this formula. So times by 2, divided by the mass of an electron, which is pretty small. Make sure to take the square root. Okay, so I get an answer of the top one there. 460,992. So it's got to be A. Oh, shit. Sorry about that. That scares me each time when that alarm system goes off. All right, so we're at A there, so good. In the same experiment, we're at, right? Yeah. In this same experiment, how many photons are produced here? All right. So we're using the second part of this question. Let me just go to the snipping tool here. I'm going to erase all this stuff that we just did. Okay. Can I get all this stuff off here? Yeah, probably not. Okay. So in the second part of the question, we have to remember that Einstein's prediction was that for every electron that comes out, there had to be at least one photon. Now, most of the photons, or maybe some of the photons, are not actually being used. They just bounce off and they do nothing because they hit the wrong electrons, right? But if an electron comes out, there was exactly one photon to go with that, right? So at least I can get the minimum number, right? That's what they asked for. Just the number of photons, okay. So I can get at least the number of photons that were used to create this current, right? So remember that current is equal to I is equal to Q over T. So if I can find the charge, remember the charge of current is made up of all of these electrons. So if I can find the charge, I can find how many electrons that is because I know how big an electron is. So I'm going to go I times T, all right? Now I'm going to use my current. My current's just fine, all right? Don't have to change that. If it was like millicurrent or milliamps, then use that or change it. But I have to change this because it's time. This is coulombs per second. So this has got to be in seconds here. So I got to go 0.5 times 60, and I get 30 seconds. Why did I do that? It's just half a minute is 30 seconds, which makes sense, right? So you got to change that, all right? So that could be a different number. So I'm going to take that. I'm going to times it by my current, okay? And I get 6 times 10 to the negative 5 coulombs. How many electrons that is? I don't know. Let's see. That is one electron is 1.6 times 10 to the negative 19 coulombs. So I just have to figure out how many fit into. So I just essentially just divide these, right? That's how many electrons it would be. All right, so I just divide the two numbers. Bam, it's a big number. I knew they're going to be big because all these numbers are big, but I want the 3.81 at the bottom there. Bam. Perfect. All right, were they all big? Yeah, they were all big. All right, so we got this Compton scattering effect here where this thing bounces straight back, and they're trying to find that final momentum. They give us a choice here. What's the next question? Oh, this one's an easy one, right? Remember, Compton used both. He used two things, conservation energy and momentum for this one. To make this formula work, he's got to do both. So that's an easy one. I'm just going to skip that one. Okay, so the magnitude of the final momentum here. So I'm just going to zoom into my picture. I'm going to just quickly take a little snapshot of this, and we're going to do a little bit of math on this one here. Okay, so what we know is we know the incident momentum, or we know the, we want to know the final momentum. Oh, of what? Of the electron? Of the electron. Okay, so this would be really easy because I have the moment wavelengths. Okay, so I know how much momentum there is before the collision. Like if I assume this is at rest, right? It's at free, initially stationary, so this v is equal to 0. Its momentum is 0. Over here, I can find the momentum of this photon by using this de Broglie/Compton formula here. H, you always use the 6.63 number 1 with this one, divided by its wavelength, make sure it's in meters. So times 10 to the negative 6, or 9, sorry, on that one. So this has an initial momentum of 5.1 times 10 to the negative 24 kilogram meters per second. Okay, so now we know the momentum, because if I add them together, the total sum is, my head's in the way here, is this number, right? It is this 5.1 times 10 to the negative 24 kilogram meters per second. So that means the momentum afterwards has got to add up to that. But we got two different directions here. So this momentum here, it's going backwards. I could do the same thing here. This is going to be a negative number in my calculation. So h again divided by its wavelength. So it's actually h over lambda. This is going to be, if I did this correctly, negative 4.911111 times 10 to the negative 24 plus whatever this question mark, it's got to add up to this 5.1 times 10 to the negative 24 kilogram meters per second again. So I'm going to take this number, I'm going to add it over. What's a weird plus there? 24. It's oddly a very nice number. Okay. Add that over, and I get 1.00 times 10 to the negative 00 times 10 to the negative 23 kilogram meters per second. Okay, so now we know, well, it's B. That's all. Okay, good. And we did this one already. Cool. Oh, this is a good, I like this one. This is a question I ask all the time. So we got this. We got three models here. They don't have Dalton's model, but we got Dalton. Then who's next, right? Dalton, Rutherford. Nope. Dalton, Thomson, Rutherford, Bohr. Thomson, Dalton, Rutherford, Bohr. Okay. So the evidence for, so this is like the plum pudding model to the orbital nuclear model to Bohr's energy levels. What evidence do they do to go from one to the other? Well, the cathode rays got us here, but to get from Thomson to Rutherford's model, Rutherford did the thin foil, right, with the gold foil, with the alpha particles. And then what phenomenon was used to change them, right? Because remember, Maxwell says that these accelerating particles should be emitting EMR. So Bohr just said, they don't do that, right? So that's going to be 6. I'm going to come back to that one. What phenomenon was used, needed to change the model? Well, it was that spectrums, right? Those absorption spectrums, the emission spectrums, all those kind of spectrums. You couldn't explain that, right? So it's got to be 3 and then 6 here. Okay. In model 1, for an atom to emit EMR, an electron would have to undergo a transition to a lower level, because it's got to go down, because it would lose energy. And the energy emitted would be equal to the difference in the states. So it's got to be C here. That's an easy question. Okay. Oh, this is a good one too. It's always good to know for the diploma what kind of things produce what kind of spectrums here. So what would it be here? So we got so which ones? So we've got a white hot piece of tungsten metal inside a glass bulb, light from the sun as seen on Earth. That's very key. It's as seen on Earth, right? Those Fraunhofer lines. Is that the one it is, Fraunhofer? I think it's Fraunhofer. The ones they see on Earth is that you see things missing because it has to pass through our atmosphere. And the neon gas. So the neon gas is obviously one that's just the emission spectrum, right? Depends on what's inside the glass bulb, right? The glass bulb is a vacuum, then, yeah, if it's just inside a glass bulb, it's just a vacuum, then the white hot's just going to produce a nice continuous spectrum, right? So the line seen from on Earth that has to pass through the atmosphere is going to absorb some of that stuff. So it's going to be 2 only, right? So Because we get crossed off 3, it can't be the bottom 2, and it won't be the top one yet. Because it's seen on Earth. Yeah. Very key, it's on Earth. When balancing the nuclear reactions in the information provided, okay. A and B, the top ones, we use conservation nucleons. All right, that's the top ones, nucleons, and the bottom ones use charge. Yeah, it seems like it would be nucleons, but we don't consider the bottom ones to be nucleons because remember we talked about beta radiation. The bottom is not a nucleon count; it's the charge of the beta particle, right? Because it's technically not a nucleon, so we say the bottoms are the nucleons, even though most of the time we're talking about like they are the protons in this case, but protons have the charge, so that's why. Okay, so nucleons charge, perfect. What's the speed of the alpha, or the speed of the neutron produced? Is this? Does it tell us information about this? Oh, it has this kinetic energy, mega electron volts. Oh, that's weird. This seems like a too easy of a question. So it's mega. Mega is a million. So this is 4 million electron volts. But you got to change it to joules. Like a couple of questions back, we had to do that. And we're talking about a neutron. Oh, maybe that's the only reason. The neutron, you have to find its mass on the formula sheet. And just using the 1/2 mv squared formula, rearrange it. And it should give us a nice number here. So let's see. Make sure you take the square root of your answer. What did I get here? I got 27 million. So I'm assuming that's right. The neutrons released in this process. Produced. Yeah. Okay, there's a lot of information here. So 277. 7. There's a lot of 7s here. 2777. That's a fun number. I wonder if you did that purposely or not. Which of the following statement best describes the neutron, the collision between the neutron and the nucleus when the neutron is absorbed by the nucleon? Which of the following best describes the collision between the neutron and the nucleus when the neutron is absorbed by that? Oh, that's a good one. What's it say down here? Fan of my computer's going to die. Let's see. I'm just reading this stuff down here. The collision of the neutron with the nucleus. The neutron, when directed at a sample, the neutron is absorbed by the nucleus. The neutron will form a new unstable isotope with a higher energy state than the original. The new isotope will undergo a transition to releasing gamma. So I'm assuming the energy is lost. Right? It gets absorbed in, becomes a new unstable thing with a higher energy state. So it's going to be inelastic because it's not conserved. I want to double check that. 32. Is that right? 32 was right. Am I right so far? Oh, man, I got everything right so far. That's nice. Okay, let's get back out of here. Return to test. All right, which of the following rows identifies the energy of the gamma photon is equal to the difference between the states? Okay. Yeah, it's kind of a repeat of a question, but this is just a practice test. They don't have to be all different. Okay. And the source of the EMR is most similar to I should zoom out here, the method that produces a hot, low-density gas? Yeah. I don't know. That seems. Just check my. Yeah, okay. Return to test. It's getting a bit late. It's 12:30. Return to test. Okay. Next one. Which of the following identifies? What is the same? Oh, it's a different question now. Okay. So 34 and the response number 10 identifies the direction of electrostatic force exerted on the free electrons in the counter and the direction of the electric field in the counter. Okay. So, photons can be directed using a proportional counter The proportional counter is filled with argon gas. Okay. An electric potential difference is applied to the counter, so the anode, which is center, is positively charged. So that's good because nowhere in the curriculum does say you have to know what an anode is and what what an anode is, because that's chemistry 30 stuff. Okay, so that means it's away from that, right? It's going away towards the cathode, because the anode is the positive charge that's coming out of that. So I can cross off towards the anode, it's going towards the cathode. Okay, so I got those electric fields going that way. What else happens here? Photons collide with the argon, causing them to become slightly ionized. So they're going to bounce out the electrons. They're going to become positively charged. The free electrons and the positive ions released by the process move in opposite direction because of the plates. Yeah. The motion of these charges constitutes current, which can be measured used to determine the energy of the photon. Okay. The ionized energy for the this is okay. They tell us what the ionization energy is. Okay. So, which of the following describes electric on the free electron? Okay, the electron is going to go towards the positive, so towards the anode, and then towards the cathode. It's the electric field. Remember, the field is different than the force. The force is which way a positive charge would go. Yeah. I'm going to just do this. Okay. So, yeah, easy peasy. Okay, I'm just going to move that on for there. And the force of this electron is just the opposite direction. I have to calculate in my hand. The maximum wavelength, so they give us the ionization energy. They just have to change this to wavelength. Hc, and you got this one, electron volts, so just leave it in electron volts. Hc over lambda, I'm going to solve for that. So H, 1.4. Just doing this one in my head. Not the hardest one. Just make sure you use the correct one here. And we got here, we want scientific notation, ABC, 791 to the negative 8. There we go. Okay. Oh, this is a fun one. Okay, so I'm going to go my calculator here. So remember, when in doubt, use your calculator to find out this. So they give you this nice little piece of graph paper here to figure out this half-life part. I'm going to use the half-life, not based on the trend of the data. That's going to be that part. But the first part here, what scale could I use? What would I use to make a great scale here? When my calculator loads up here, there's my calculator. Close this here. Okay, so we're going to use a calculator to get the half-life part, but I'm going to look at the scale. So I want the time on the bottom to use as much as possible, and I don't want to use some weird numbers for my scale. Okay, so we try to avoid numbers like 3 and 6 and 8 and stuff. We like to go 2, 5s, and 10s, 20s and stuff like that. Nice numbers that divide by 10 or 5s nicely, because they look like here there's a 10 division here. Okay, so on the bottom, I want time. I have to go up to at least 8. So I got to double check. 1, 2, 3, 4, 5, 6, 7, 8. So 2 would be a nice spot for 8, actually. I think 2 is good. You're going to go up to 10. Right? You're going to go beyond what you need. That's okay. You're using about 80% on the bottom. And then I need to get up to at least 15-ish on this other one. 5, 10, 15. Nope. 5, 10, 15. So ooh, that would be nice to have a 5 there. 5, 10, 15. Skipping 2s, right? And then you can divide that by 2, 10 pretty easily. So I'm going to say that's going to be a good 5. Like 2 on the bottom, 5 on that one. Now I'm not going to graph it on there. That's just weird. Who would do that, right? So you're going to go to your calculator and you're going to put this information into your calculator, right? So assuming your calculator has been reset at this point, so say it has, right? I'm having problems resetting my calculator. There's something weird in my, oh, that's why this thing's right in the way. That's probably why. There we go. Ah, perfect. Okay. So I'm going to reset. I'm actually just going to clear all my lists here. Oh, poop. Okay, I'm gonna clear all my lists, get rid of all this. Okay, so I'm gonna go stat, I'm gonna go edit, and I'm gonna put all the information into here. So go stat, edit, L1 is gonna be X's, L2 is gonna be your Y's. So I'm gonna have 0, 2, 4, 6, 8. And then in my other column over here, I'm going to just type in what I have here. So 14.5, 8.5, 5, 2.9, 1.7. Okay. And then I'm just going to double check that. Looks pretty good. I'm going to go y is equal to. I'm going to get rid of all this garbage that's in here. I'm going to go to plot 1. I'm going to turn that on. Plot 1 plots L1 and L2 as X and Y. So I can see what this looks like. And we're going to go zoom stat. So there's my graph. Oh, it looks really nice. Yeah, you can see where the y-axis is and all that stuff. And then what I want to do is I want to graph this. I want to see how the regression looks. So I'm going to go stat. I'm going to go over to calculation. I'm going to do a regression because this is a half-life regression. Right? Is this half-life? Yep, half-life. It's going to be an exponential. So I'm going to scroll down here, find exponential. There's EXP regression. I'm going to use this one, and I'm going to store this equation. Now, depending on your calculator, you may have to go to VARs and find it, or if you have one of these newer calculators, go alpha, trace, and then I can pick number 1 there. Okay, and I'm going to hit calculate. Okay, there's my equation. This A value is my initial amount, which is going to be useful because I want to have that number to find the half-life of this chemical. So if I go back to y is equal to, or sorry, graph, sorry, you can see there's my graph. Oh, it fits really nicely in there. Okay, so I'm going to go to my other graph here, my y is equal to, I'm going to take this initial amount right here, lots and lots of decimal places, and I'm going to have it. Right, this is the A value is your initial amount. And you want to find the half-life, so you want to find the time it takes to get to half of this number. I'm going a little bit excessive here. Like I'm literally typing out that whole number. I can see that it matches really nicely there. I'm going to hit that. I'm going to hit graph, and you can see there's my halfway line. I want to find out that time that it takes to get there, because that's the time it halves. So that's your half-life. All right, so I'll go second trace, intersect, enter, enter, enter. And there it is, 2.6. I'm going to round that up, 2.6. Like perfect, 2.6. And hopefully if you graphed it by hand, you'd also get 2.6. Maybe not, I don't know. Next. All right, so thorium's half-life is this. What percentage will be left after this? So remember that in the formula, I'm going to write this one out. Remember, in our formula here for half-life, the formula says N, this is the one on your formula sheet, N is equal to N naught 1/2 to the power of N. There's a lot of N's here. Now, N naught is the initial amount. We're trying to find percentage. So I'm going to say that's 100%. All right, we're going to start off with 100%, and then I want to know how much is left over. But this N at the top here, this is how many half-lives have occurred. And I can see the half-life is 24 days, but there's only been 18 days, so it's not even a half yet. Right? So I'm going to say it's either C or D that's left over, right? Because I haven't even got to a half-life. If it's been 24 days, it would be 50%. So it's got to be less than that. Or sorry, more than that left over. So to find this out, this is just going to be T over P. If you remember your math, 30 days. But if you don't, T over P. So this is going to be time, 18, over 24.1. You have to make sure that both days, if they're not days, both days, make sure they both are, or they're just both the same units. They can be both the years, both be decades, both be seconds, whatever. Okay, so 1/2 to the power of that, and then times it by 100. Okay, 59. Yeah, that makes sense. 59.6. So it's going to be C. Okay. Increasing energy per unit mass, very important, per unit mass, right? So I don't have to do any math for this question. I just have to recognize what's what here. So 2 is a hydrocarbon combustion. Very inefficient, right? So that's going to be the bottom of my things increasing. I want to go up to the higher number. So it's got to be A or B. Okay. Then remember it goes fission, then fusion. So fission is 3. We got a big guy becoming 2 smaller ones. So it's got to be B. Fusion's 2 smaller becoming a bigger. Okay. How much energy is released? Okay, so to do the energy released one, so we have to remember how this works. This is for reaction 3. So I'm not concerned about the other reactions here. Just worried about reaction 3. Okay, to find the energy released here, I'm going to have to find the mass before and the mass after, because there's going to be a difference between the two. So the mass before is going to be 1 neutron and 1 uranium. So I'm going to take 1 neutron, 1.674927 times 10 to the negative 27 kilograms. That's 1 neutron. I'm going to add in a uranium here, 3.902996 times 10 to the negative 25 kilograms. And that's going to be my total mass before. Then I'm going to look at my mass afterwards. Right? I don't know where I'm going to put this. I'll put it over here. Okay. And I can see that this is 1 barium. So I'm going to add in a barium. Lots of numbers in these ones. You get lots of time. Take your time. Make sure you do these correctly. Don't try to rush through it. You don't get an achievement for being fast. Right? The government just uses the time data at the end. So be honest when you complete the test how long it took you to do it. They just use that to figure out outliers. Like, oh, did the kid take 30 minutes to actually do the test? You probably shouldn't be too reliant on his information when it comes to results and stuff. Because the governments love statistics for some reason. Okay, so you notice I went 3 times my neutrons there. So 3 times the neutrons. So you got to make sure you have 3 of those, and the other one's at 1. You can probably cancel out one of those and just ignore it because you are going to minus these 2 numbers anyway. Maybe I'll do that. No, I won't. I'll just do the whole math here. Boo, ba, boo, 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 boo. Okay, negative 27 plus 2. So yeah, so lots of button pressing. I could almost just pause the video and do this. Okay, but I'm not. So the mass before this reaction, we're going to have to write them down here. So 3.91974.527 times 10 to the negative 25 kilograms. Okay, and then afterwards, okay, don't make sound effects while you're doing this during the diploma. You're going to make a lot of enemies. All right, and then I'm going to add in 3 of these particles, 3 neutrons there. Did I tip that in right? 6. Yep, okay. Tips in negative 27. You have time, like I said. Take your time when you're doing these. Try not to rush it. You might type in one of these ones. Sig digs a little bit off here. They got lots of sig digs here, but I think they only want a very specific amount. Oh no, my head's in the way. Okay, so what I need to find here is my change of energy, which means I need my mass defect times the change in the mass. So what is the change in the mass? I'm going to subtract these 2 numbers. All right, so 3.91974527, yep, e to the negative 25. And I get a change in mass to be minus, because final minus initial, 3.9, nope, that's 3.08846 times 10 to the negative 28 kilograms. Everything's in kilograms, which is nice, so I don't have to worry about changing these units. Because if these are all atomic mass units, then you have to change that at the end before you put them in this formula, E is equal to mc squared. I'm going to take this. You know, the mass went down, but that means the energy went up. So even though the mass is negative, I don't care about that. I'm just worried about the positive energy change here. This is going to be in joules. So this is going to be 2.7796. Oop, that's supposed to be a 9. 9614 times 10 to the negative 11 joules. Okay, so now we have the energy in joules. Is that what I want? Yeah, I want it in joules. Sweet. Okay, so they just want 2 sig digs and 2 decimal places here. So let's go back to my number here. So I get 2.8 times 10 to the negative 11. So 2811. 2811. Sweet. Next. All right, so we got the cyclotron here, going around and around and around in circles here. You got the separation gap here. This is the last question, isn't it? Yeah, because this is going to be a two-parter. It's a big one. I've done this one in class before. It's a big one. You have to think about the physics principles that were used, what was done first, what was done second. Okay. So I want to figure out what is the radius of curvature after it crosses the d-separation described here. So it comes in with initial velocity. I want to know what its final velocity is, et cetera, et cetera. This is a proton, so there's lots of information here. I'm going to zoom in just to the bottom part of this, because that's where all the information is. So right here. All right, I'm going to snip into this part right here. Okay. Actually, I really only want this part right here. But I'll describe it as I go. Okay. Boop, 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 boop. Let's cut the picture in half. Okay. Okay, so what's going to happen here? So as in one particular section of this, there's charge plates. It's got the protons going between these two. It's got this magnetic field that's causing this circular motion. That never changes. So what I want to find here, my goal is to find the radius. How do I get the r? Right? That's my goal. That's my final thing that I want to do. But to get that, I have to think about, okay, what's causing this circular motion there? So what's causing the circular motion is my magnetic force. So I could say Fc is equal to Fm. Fc being the net force. There's only one force here, just magnetic force. We probably ignore gravity. It's probably going to be small enough that it's not going to affect anything. Plus also it's going the other direction. Not going this way. It's not going around circles. Don't worry about it. Okay. So Fc, which is an F net, is equal to m times a. You got QVB. Okay. And this is m times, and that, because we have speed, we're going to have to find the speed. This is going to be my final speed. This is my final speed there. Squared. It's equal to QV. B. I can cross off one of these here, and now I can solve for r. So I can times up the r and divide down the q and the b. Okay, so this looks familiar. We've done this before. So what do I need? So I had the mass of a proton. Good. Charge of a proton. Good. Those are my formula sheet. I got the magnetic field. Yes. I need to know the speed. So this is not the first thing I'm doing. This is actually the last thing I'm doing. This is step 2, essentially, right? Dealing with circular motion. Before I get there, I got to figure out what is this speed. It's not the initial speed because I have to use the final speed. This is after it's got there. So I got to find out what this final speed is. Right? So I got to do this. So, thinking final speed, maybe I can use some kinematics, right? Got initial speed, maybe I can find the acceleration. I got the distance it has to travel. I can use that to find the final speed. Or I can use energy, because there's going to be some kind of conservation of energy. I'm going to lose potential. I'm going to gain kinetic conservation of energy. Okay, so I like the energy way of doing this question, because I got voltage here. Awesome. And remember, I can find the change of energy. Actually, I'm going to start over here because it might require a little bit more work, by using this formula. So the change of energy is going to be equal to delta V times Q. And I know the charge of a proton. I know this number of mega electron volts here. So I can put that number in there, times 10 to the 6 volts, times the charge of a proton, which is the same as an electron, just positive. You know what was missing here was all the quirks and stuff. That's okay. You can't have all the questions like that, because this is the last question, so we're near the end. So the change of energy here is going to be 3.2 times 10 to the negative 14 joules. Okay, so remember that change of energy is equal to final, oh, I have to move that down there somewhere. There you go. Final minus initial. And remember, this is going to be change of energy, but what type? Well, because we're talking about speeds here, this is going to be change of kinetic. It could be change of potential because we are losing potential energy as we go through this. But as we lose potential, we gain kinetic. So we can say that this is kinetic energy as well. And we can't say our kinetic energy starts off at 0 because it gives us an initial speed. So we're going to have to find out what that is first. So what is that? It's going to be 1/2 mvi squared, right? So when I go final minus initial, it's got to be this change. So you can see that I'm just going to add this over eventually, but maybe I want to find out what that is beforehand. So 1/2 times the mass of a proton. So a proton, 1.67 times 10 to the negative 27. It's not an electron, it's a proton. Times the speed, it has it right there, 2.5 million meters per second squared. So make sure to square that. So it starts off with 5.21 times 10 to the negative 15 joules. So what I'm going to do is I'm going to add over that number, put it that side, because right now it's minus that number, so I'm going to add it over the other side, and I'm going to get the new final energy, because I'm increasing by quite a bit here. So my final energy is going to be 3.721, I got lots of decimals here, negative 14 joules. Okay, so then I'm going to take that and find the final speed. This is equal to 1/2 mv squared. It's equal to this number. Let's call it EK for now. And I can find the final speed by rearranging this equation. 2 times the EK divided by the mass. Okay. So, times by 2 divided by the mass of a proton. It's just on my formula sheet. 1.67 times 10 to the negative 27. Okay? Take the square root. So now we have the final speed. So our final speed here is 6,627,327.3 meters per second. Okay, now I can take that. So this is the first thing I did. The first thing I did was dealing with the change of the energy. Then I can take that over to the other formula there. I got a mass of a proton, I got the charge of a proton, just plug it all in there. So I'm going to take my speed times my mass, divided by my charge, and my Teslas at the same time there. Okay, so I get a radius here of, after I do all that math there, plug all those numbers in. I'm not going to write those all out. So 0.0800746. Blah, 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 meters. Okay, so they probably want numeric response here, right? Yep. So they want this to be 8.07 times 10 to the negative 2 meters. It'd be nice if it was just centimeters. So 8072. 8072. Because they want the 3 sig digs and the exponent. 8072. I think that's what I said, right? Yep. Cool. Now, what did I do first? Okay. So this is using those things at the bottom of your formula sheet here. No, sorry about the slushy. You got that wet there. But I got 0 to 9. You got all these little principles here. What did we do first? So even though I thought about this question in reverse, because that's usually how you do these bigger questions, you have to think about it in reverse. I didn't do that calculation first. I did the calculation that was over there first, right? That calculation involved energy, conservation of energy. So that's going to be 5, right? So I used a conservation of energy there. The energy that was lost was gained, potential energy, or potential energy was lost, was gained as kinetic energy. So I'm going to say that's 5. Uh-oh. My computer. Oh, cancel. Uh-oh. What happened to my computer? Did I lose my computer, guys?